There we go. So this chapter was actually pretty significantly different from the previous one, at least in my opinion. The previous one kind of just laying out the goals of the book and explaining a little bit about the properties that we were going to explore throughout this book. And then this one, in my mind, was a little bit chaotic. I don't know if other people felt the same way. It was kind of introducing a lot of different topics and going very in depth on certain ones and then staying fairly shallow on other things. Um, and the big thing that it was teaching us was the data models and query languages. And so it kind of gave us an overview of a lot of different technologies that are going on. In the first section, they were basically just saying there's a lot of different abstractions, and very commonly we're going through different data layers. Hang on, let me make this a little bit bigger. And so you might go from app code to database to bytes, and then you can even go further than that to electrical current. And so we're going through multiple different layers of abstraction. And so you might be writing something, but then you might be calling a library or a database or something else that's kind of adding in a whole extra layer of complexity that you're not even interacting with. And understanding these and how they're designed is pretty central to how we solve problems and how we even think about them. So if data is formatted in one way, you might kind of think about it in a certain way and solve the problem using one method. And then if you had it organized in an entirely different way, you might solve it some other way. So the two models they focused in on right off the bat is the relational model. So this is SQL. Most people are probably more familiar with that. And then document models, and then they also mentioned network or hierarchical models. And so the core premise of SQL is that data is organized into relationships, and then it does a whole bunch of magic in the background to hide the underlying implementations from you. So you just say, I want this data, and then it figures out specifically how to efficiently query that data. And then they talked a little bit about, I don't know how you guys prefer to say it, SQL, NoSQL, SQL, et cetera. There's many different ways that I've heard people say it. But they started talking about NoSQL, and its primary goal that they laid out was to handle greater scalability and really high write throughput. And it's not necessarily a rule, but it seems like the options on that side tend towards open source and free over commercial. On the SQL side, you more commonly have paid for options. And then one of its big advantages is very often it has some sort of special queries that allow you additional functionality that you aren't able to use with just standard SQL. And then in the next section, they were talking about object relational mismatch, and they defined the term impedance mismatch. And so basically what they're saying is that sometimes the structure of SQL might not match reality of application code. So the example they showed is you might have some list of something, and then that becomes a certain column in your database, but then in actuality, it's storing multiple things, or it's not standardized necessarily. And so you might have to do something in your application code that actually handles that and does something special with it, and it adds some additional footwork on your part. So the example they used is on LinkedIn, for example, you might have people have multiple previous jobs, or they might be working multiple jobs currently. And so if it's captured in a single column, then you might not have a way to really capture like these are their previous jobs, and there can be many of them. It would just all get bundled into a single column. And so they were stating that the document-oriented databases might help that in some way. I see chat going off. Any questions? Any reasons to stop?
No, it's just chit chat.
Okay. Feel free to chime in if anyone has any additional history. This is actually one of the first times we've done book club, and I'm legitimately learning a lot of new stuff because it's not some concepts I've been exposed to before. So if I get anything wrong, or if anyone wants to add anything, feel free to hop in at any time.
I just want to add that NoSQL does not mean that SQL is forbidden on some system. It actually means not only SQL, meaning that it is just another database, and quite often people use it because they cannot use SQL, which is, well, has worked out very well, has a lot of advantages, have quite a nice history of usage and such and such. And okay, and another example of NoSQL database is a graph. In a graph, we have connected nodes, which mean that the number of possible edges between nodes is quadratic to the number of nodes itself. But the thing is, if you have, for example, a map of cities, then not each node is connected to each other. You have only few connections for each node to others. So for graph database, SQL implementation is not very good. And besides, if you want to make some kind of road through several cities, in SQL, it would mean that you need to do several joins, and joins in SQL are very expensive. So in this case, graph database is preferable.
Thanks.
By the way, I have a friend who says, mostly seriously, I mean, kind of half joking, but mostly seriously, that he knows that a storage technology is mature when there's an SQL interface for it. So like for MapReduce, right? It's mature when you have Hive, when you have a way where you can write SQL and you can hit it.
Well, now they have BigQuery, which is full like SQL standard. So it's completely matured then. And that's an interesting counter to this NoSQL stuff is the SQL is hybridizing the NoSQL approach. So
and I think actually that's part of, I think that's part of the author's point, that it would be a mistake to have a debate about whether this database is better than that database because of the query language, that maybe there's some advantages from the underlying representation that will be more efficient for your use case, and that ultimately you may get the query language that you like as a front end for that underlying storage technology, that they're really two separate things.
Yeah, and they kind of separated the two in the book too, because they were saying back at the top data models and query languages, and they aren't necessarily tightly coupled all the time. Sometimes you can actually query in one language and then it basically gets converted to the other. And the important thing is the underlying data model and how it's optimized for your specific access patterns.
Yeah, I mean, he didn't say it, but I was reading between the lines that he's heard people arguing, and he's like, no, you're arguing about the wrong thing. You know, like he showed those two, neither of which I knew, the cipher and the data log or whatever, you know. And, you know, he was kind of saying like, well, if you look at it, they're pretty similar. The punctuation's different, but conceptually, you know, they're these, you know, similar query languages.
Yeah, I am curious to just because I'm in this space more deeply on the data warehousing and sort of streaming data side, whether some of the optimization that's already happening in this space of sort of moving stuff around and moving into memory, if that ends up eclipsing some of the graph database advantages, it can now watch your query patterns and make those joins, right, that Maya was bringing up cheap, because it can put some of that stuff in memory.
Yeah. So then in the next section, they were talking about many-to-one and many-to-many relationships. And so one of the things they were talking about is let's say you have some text field or something like that, and someone says Seattle, and someone says Greater Seattle, and someone says Greater Seattle area. You can, in some way, map those all to the same ID, and then it makes it more convenient for doing joins and various other operations down the road. But then you also might have to do some mapping between all of those values down to a common ID. So you're kind of shuffling around the complexity. But that might be good for you if you have something where, like the example they were saying is maybe something due to political reasons, Seattle turns into some other name, and then you can just change the ID. You don't have to change every single individual record. You just basically say, change the ID that it maps to. So I think there's pros and cons there. You're moving around where the complex point is. Then they talked about our document database is repeating history, and they looked a little bit about previous attempts at these sort of alternate approaches instead of the relational approach. They talked about IMS from IBM, and they were showing that basically it had similar faults to the current document models. And then they talked about the network model. I don't know how this is said. I would say codicil, which allowed you to allowed a record to have multiple parents. And so that was kind of what they were talking about, where greater Seattle area could be linked to every user in that region. So it has a lot of outward connections, basically. But then it was difficult to access individual records because you had to go down the full chain of command, basically, to get to that individual point. And so contrasting that to the relational model, which is just a table and it's just a collection of tuples. So that's kind of the common CSV style format that we're familiar with. You open something up in Excel and that's what it's going to look like. And it has much simpler read operations. It's just columns and rows, and you can just say, I just want this column, or I just want this row, and you can select those in various different ways. And then you have the query optimizer that is finding the actual optimal way to grab those. So you just basically give it some condition, and then it will go and find the best way to actually grab those rows or columns. Then they were talking about relational versus document databases. And so they were saying that the document model favors flexibility, better performance via locality, and closer to application representation. And so that was a lot of the stuff that we've talked about. It gives you, the document model allows you to basically just put a whole bunch of data in there, and then when you actually read it back, you can decide what to do with it, and you're not rigidly defined by whatever schema you might have put in place ahead of time. So for example, in the LinkedIn example, if you defined a schema and you said, here's our previous job column, you don't really have much way to alter that and say, oh, now I realize people might have multiple previous jobs. You'd have to potentially add additional columns or do other operations. Whereas in the document database model, you might be able to just put the data in there in its raw format, and then when you actually read it back, you decide what to do with it and how to load it in and separate it into multiple previous jobs. And you can have variable amounts of entries there. And so the locality, it just stores all of it together, and then it's closer to the application representation, because when you actually load it in, you can have it represented the same way that you actually want it to. And then the major benefits that they got from that they mentioned from the relational model is that it supports joins, and it's better for many-to-one and many-to-many relationships natively. You can do those, you can query basically any data you want with any method. It's just about how efficient and how convenient it is. And that's a bit easier when you do it with the relational model. And then they asked the question, which data model leads to simpler application code? And it really just depends on your use case. It's kind of difficult to prescribe this one is specifically better all the time, or this one is better for this use case or something like that. It depends on how your data is formatted going in and how you want it to come back out. So it's kind of an ambiguous question. You just have to analyze on a case-by-case basis. And then the document model allows data to go into the DB without a schema. And so they talked a little bit about the schema is applied on read. So that was what I was talking about a little bit earlier. You just basically stuff data in there, and then when you pull it back out, you decide what it's supposed to look like. You don't have to rigidly say this column gets this data and then so on, and have all of that predefined. And that's helpful for I'm pretty sure that should say heterogeneous. So new unseen things can come in, or you want to add additional information or whatever, and that allows a bit more flexibility there. But then the issue with that potentially is if you go to read some data and you have to read the entire document and then you only want some piece of it, that can be potentially detrimental. If you say, I'm loading the entire document, but I actually only wanted their name or something like that, and you also have some full history of something else, then it can be detrimental to have your data organized in such a way, because it's not easy to query just a specific thing that you're interested in.
I can give you an example of that, Ryan.
Yeah.
So we have these patient charts from all the people that we see. And so somebody said, I'm not sure if this particular thing that we ask patients is useful. How many times last year did somebody ever actually say yes to this question? And they were like, IT was like, we just need to read every document to go down to that one question to see whether it was yes or no, and like it'll bring the system to its knees. It's like, really?
Then I have a follow-up question on that, Ted. I think that we are probably on the opposite direction of what you have there. Like, I'm trying to understand whether or not, would it make sense to have a combination of both? Like because our current model is entirely relational, but then it creates a huge, like with practically like what Ryan said, that you essentially put everything that you've in the data right now, everything matters, right? Like you make it into the columns, but it creates like in some of our survey data file, we have 9,000 columns. I don't even know, like, we're using Redshift and there's like 1,600 limit, and you kind of have to think about different ways anyway. But my question is, I don't even know how many of the 9,000 columns variables are supposed to be useful. So how do I handle that? Like, do you guys have any kind of recommendation? Like, is it a combination of document and relational? By the way, I'm a super non-technical person, so I don't deal with database coding or anything like that.
Does anybody else have a strong opinion?
Could you repeat the question?
So the question is, we kind of have the same kind of data like Ted described, right? I think that you have patient charts, but we have surveys, right? So there could be a 45-minute survey, believe it or not, that kind of translates into 9,000 variables for any given respondent, like any given individual. Now we have a decision to make when we load that data into the database. Are we going to, based on what Ryan described and what the book describes, it seems like, okay, if you don't know what to do about these columns and variables, maybe the most efficient way to load it is the document model. But then downstream, you kind of have to pull things out, exactly like what Ted mentioned, like how many times or how many people have answered this question in a certain way. And we want to quickly get to those kind of joins and whatnot. I think our biggest current issue is that we have no way to store the 9,000 columns. There's just no way. So, and Redshift has always been saying, like AWS saying that it's better to store these things as rows instead of columns.
So,
yeah.
So like some of newer databases, like I know Postgres actually supports JSON fields. So like if you have a Postgres database, like you could have some of it in a relational database. And when you're designing a relational database, you actually get to choose how normalized it is. So normalization is common practice and you should be normalizing your data. But if you wanted to, instead of, people usually normalize to at least a third normal form. But if you want to, if you have X number of fields, you could put it, instead of having like 20 or 30 tables, if you're worried about performance, you could have like 4 tables and you could just have duplicate fields. That's not best practice. We can do that, but it depends. Like sometimes you might have a document database that connects to a relational database. It really depends on what your performance goals are and what your latency, like what amount of latency. Because if you do a document database for something and you don't have as many, it's not very relational data, you're going to get better. You're just going to get better performance. But if this is more for data warehousing and it's not an OLTP, it's not online transactional processing, then there's a lot of different things you can decide. And then basically, if it's relational data and the data model ahead of time, I would say almost always choose a relational database if you aren't.
I see.
If it's relational, but if you're not sure about the schema or the schema is going to change, and it's a lot of data and it's not as relational or it's just not as many relations, I would choose a document database. But then there's also stuff which is technically NoSQL, like graph databases too. So if you have tons and tons of relations, you might want to choose a graph database, which is a whole different data model. But I guess what I'm trying to say is you can choose how normalized a RDS or a relational database is. So you do have some options. It's just a series of trade-offs.
Right. And I know this kind of question definitely always has a lot of nuances. And so it depends on a lot of factors. And that's actually one question I have when I'm reading the book, right? Like maybe you guys, because you guys all have the technical background, you already kind of know from your hands-on experience, like what kind of factors will drive more of your decision to go with a certain data model or data type of database or not. For people like me, this will be completely like I don't even know how to make the decision right now.
Yeah.
So Becky, here's my 2 cents worth. It depends what you're trying to optimize for, right? So we used MongoDB, which is a NoSQL database at my last company, and we went through an interesting evolution there. So originally, and this is before I got there, we were basically putting, again, it was patient information, and we're putting all of their visits and all of their labs, et cetera, into one document. And the concept was that when it was time for us to run a bunch of rules, we would just be able to pull out the patient. And by doing one single read, we would have all of the patient information plus all of their visits and their labs and all that sort of stuff. So there, that decision was made, and I'll explain in a second that we actually had to veer away from that decision, but that decision was made because what we're trying to optimize for was processing speed, right? We have millions of patients that we have to do, and I don't want to have to go and read the patient record multiple times, right? So I just want to be able to load the patient once, run a bunch of basically algorithms against that one patient, right, for a bunch of rules, and then I'm done, and I move on to the next patient. Right, so there we were trying to optimize for processing speed, right? Because we had SLAs that we were going to do, the entire population in X number of hours, et cetera, et cetera. So I think what ended up happening there, and this is now an implementation detail rather than a design detail, is we found out that there were limits in MongoDB to how nested the data could be, right? And how much each document could hold. So then we actually ended up having to break it out into separate collections and effectively do this kind of relational model in MongoDB, but it was the application that did the relating of the different things, sort of thing. And that was, again, that was a technical implementation constraint rather than a design constraint, so to speak. Okay, so that's the first thing. The second thing is, if you want to figure out which columns, you've got 9,000 columns, right, that you just said, which columns are useful to you or not, I would suspect that what you want to do is you want to put it into a database that has a schema on write rather than a schema on read. And the reason for that being is you can then run statistics on those databases, because since they know what the data types are, because the data types are typically primitives. And what I mean by that is when it stores the columns, it knows that this column is a string, this column is a date, this column is a, a Boolean or whatever. You can then run statistics on those databases later to figure out which columns am I actually using and which columns am I not using, right? Which will then allow you to make optimizations further down the line. But that comes back to that question that I started off with, is depends what you're optimizing for.
Gotcha.
Yeah, so what I would say, I mean, in the book, right, I think the exact words the author uses are, it depends. It depends on use case, right? But I would say that if you look at your usage patterns, there's a few extreme cases where you know what you're going to use, okay? So for online transaction processing, so it's like a bank, it's deposit $15, withdraw, $25. You need a relational database for that type of transaction processing system, okay? In the extreme where you have ridiculously high volumes of writes, you're probably going to go to some document database, okay? And in the extreme where you have constantly changing content and it's too difficult to change the schema. So I don't know if Facebook, LinkedIn are constantly evolving what is on a page, what person can submit, what kinds of information we're storing, then you're probably going to have a hard time managing the enforced schema of really, but you're in between clearly, right? But I would agree with Stephen and Keegan, and I would say that you're not in a super high volume situation. You're probably going to want some kind of relationally kind of thing. It doesn't necessarily need to be old school relational only, but you're probably going to want something where you do the statistics, you can have indexes, and you can basically optimize so that you can optimize for when someone says, what are all the answers from this particular survey on question 17?
Right.
That then you can pull back the 10,000 people who responded to that survey and how did they do on question 17. And if it's not fast, somebody can index it, they can optimize it to make that fast. Whereas if you go in the extreme for a really, really basic vanilla MongoDB, then there isn't necessarily an easy way to optimize that.
So you guys don't have a situation where you actually, like, for example, use a document DB to house the data, and then downstream that you kind of pull that into a relational database and do your transformation there?
Oh, I mean, you'll see lots of clever things in the book, and then ultimately, if people here know that there's use cases where basically companies build their own special structures, where this part of it looks a little bit like a document store, but then this part looks like it's indexed like a relational database, and but again, those usually are because people have some kind of high volume, some kind of performance that they need. In your case, I really don't think it should be that difficult to just put it in a SQL database and create a few indexes, because I imagine that your write activity, the amount that you insert or update the database, is fairly slow, fairly minimal. So you could optimize the indexes for reading. You could optimize the hell out of it.
Right. And Becky, I mean, again, I don't know your business and exactly how the data flows through your business, but I think Keegan kind of touched on this earlier, which is you could set up a data lake or a lake house kind of thing where the initial data is stored in whatever format you want. And then as you figure out the columns that are really useful for you, you put those into a data mart that may be more relational sort of thing that then can serve out the business for people who are actually doing queries using some sort of business intelligence tool. like Tableau or, you name it, you pick your tool or Power BI, and they're hitting the relational data mart that's downstream from just the raw data that got dumped into the data lake.
Yep. Definitely agree. Thank you guys for the input there.
Thanks for the question, Becky. You got everyone excited to talk. That's always useful to get some good discussion out. Continuing on, so one of the things that Becky and some of the other people in the conversation that led after that was sometimes there's a mixture of that now. So you might have a relational database that also has aspects of XML or JSON inside of it that allows you to capture some of that document modelness inside of it. So it might be possible to do some sort of hybrid type method where you have certain things that are relational, and then within those columns you might have something that's XML or JSON that can capture a document or some sort of organization like that, where it's a little bit more flexible. And so they likened it to static versus dynamic typing in programming. Then in the next section, they were talking about the query languages for data, and they laid out two separate types, so declarative and imperative. Declarative, you specify the data pattern, and then the query optimizer tries to find the optimal way to find the data that matches that pattern. And so they were kind of explaining that as like relational algebra. You basically say, I want data that meets this condition, and then the query optimizer will actually do a bunch of magic in the background to try and find the best way to pull that out. And it's more easily parallelized because it's all done in the background. You don't have to actually write that code. There's probably a lot of sophistication that goes on there, but you don't have to actually write it. So it's easier to just have someone else do the work, or the pre-written code do it. And then the imperative query languages, it's much more verbose. You're explicitly coding all of the different operations that are happening. And then it's harder to write the parallel code because of that. You'd have to actually write the parallel code yourself. But it also gives you a little bit more flexibility because you're defining specifically what happens. And then they had a section on declarative queries on the web. I didn't find this section to be that useful. I don't know if maybe it's more useful for people who do a lot of web development, but they were kind of showing there's even this difference of declarative versus imperative just in different, I don't know what to call them, but CSS, XSL versus JavaScript. I don't know how I would name both of those together, but.
So can I make a comment about that, Ryan?
Yeah.
So I was building web applications like in the late 90s, early 2000s, and we didn't have really great CSS, XSL capabilities. And so I was literally writing JavaScript that would say, for example, we wanted a table to have alternate row shading, and so it was literally like, if row number is even, color light gray. If row number is odd, color dark gray. And so what he's talking about, like, I had to write that imperative code, and it sucked, as opposed to, you could just say in whatever these, style sheets, like row number even white, row number even dark gray, and it just does that. And then we'd have like errors in the code where you do something and a row gets added to the table, and then you didn't think of that use case, and now you have two light gray rows in a row instead of alternate shade. It really sucked.
Yeah.
So at least for me, that example made sense. The difference between saying how to do it and here's instructions to stepwise do it versus just declaring the properties of what you want.
Yeah. I have done some stuff in that area, but recently the most interaction I've had with all of the different web technologies is when I do random web scraping things and I'm trying to just extract a specific piece of information from a page. Like I'm saying, grab all the paragraph tags or grab all of the whatever. And I nearly have an aneurysm every single time because it's so annoying to make it grab one thing and not the other thing. And then I also get the surrounding tags and the whatever else. So I can appreciate the complexity there.
And maybe this is in a similar vein, Ryan, but to sort of point out the crossover between these two models, modern kind of front ends, right, use JavaScript a lot to manipulate CSS tags. So they're using the declarative structure that you're using for styling to make the page more dynamic in some way, right? And so I think there's a lot of hybridization between these two models as well.
Yeah, yeah. Combining the two. And then they talked about MapReduce querying. It sounded like they were going to discuss this more in later chapters, so I didn't really spend too much time trying to specifically suss out too much information from this. I took a online class on Coursera on big data a while ago, and they made us write various things with MapReduce, and it was always a bit opaque to me. I finally understood it a little bit by the end, but I'm hoping in later chapters they'll describe it a bit more thoroughly. The way they were describing it is somewhere in between imperative and declarative, so it kind of combines the two with the map and the reduce, covering a bit of both of them. And so they're basically saying with MapReduce, you write two separate tasks. These are functions that do slightly different things, but they are self-contained units. They can't have external information. They can't be looking at other rows. They can't be doing other things. And then you use the two of them together in order to grab the data you want and filter it in some specific way. I don't know if anyone else has anything they want to add on top of that.
I mean, just to niggle on this, in a reduce operation, you're always dealing. Hopefully, you're dealing with more than one row in most scenarios, right? So you're dealing with them in some sort of chunk, right? And then those chunks are sort of being combined. If anybody's ever done merge sort, it's very similar to that.
So I think, Ryan, the way I would summarize the, not explaining the details, but just summarize the key concept of MapReduce is that we had computers, and back then they weren't very fast at all. And so then you were limited on how much you could compute. So at first people said, well, what if you just have multiple computers and you break up the data? That didn't work very well because usually there was dependencies between different parts. Okay, and so it just became very difficult to write a program that could actually run on 16 computers and divide things up and whatever. There had to be some kind of communication between them. So then the idea of MapReduce, the fundamental new idea was, rather than moving data to computers, we're actually, the concept at least, was we're moving compute to where the data is. So if we divide up our data into 16 different physical storage nodes, then you say, I want you to do certain computation on this. And so it could be things that it can just do locally. It can compute the sum of two columns. It can do whatever. It can turn a name into all lowercase. It can do that just fine locally. But then at some point, when you need to compute, the way they abstracted a very clean way that they could talk is if you have a reduce operation. So if you say sum, then you can just sum what you have locally, and then they sort of aggregate it all together into a total sum. But there's certain concepts that are very difficult to turn into a MapReduce phenomenon, right?
One of the tasks I remember from the class that I took was They basically, I'm not sure if I'm remembering this correctly, but I think they tried to make us do a matrix multiplication using MapReduce. And I just remember that being very difficult for me to reason about.
Yeah, so basically, if you've got your data spread out, then you sort of are figuring out which local chunks do I have, what things can I do, and then you are sort of like summing things or whatever in different ways, you know. But yes, matrix multiplication is non-trivial. It's a lot more complicated than just like sum or average, right? Because average, you just do two reduces. You do a sum of everything, and you do a count of everything, and then locally, once you have those boiled down to single numbers, you can divide the sum by the count, and then you have the mean, right? Much simpler than matrix multiplication. But that's ultimately why, getting ahead a little bit, but that's ultimately why people were very happy to move from writing explicit MapReduce code to using something like Spark. Life got a lot easier.
Yeah, and another instructive pathological case is ordering or ranking, right, in a distributed manner. So that sort of gives some intuition around these are the kinds of things that are really hard.
Yeah, sorting doesn't really align with MapReduce well at all. I mean, you can do it, but it's not natural to the MapReduce.
Yeah, I think again on the data warehouse side, Google's doing some interesting things too. Essentially, if you really want to rank, right, or you really want to do some of these types of operations that are expensive, then you tell it, well, as long as I'm within 2 or 3%, I'm fine, and then it can give you an answer because it can do clever things right on each machine to estimate when it's combining things.
But if you imagine earlier, back when, if you just wanted to know how many of these 100 million web pages talk about cats, you can do that with MapReduce. Because you're just each locally saying how many cat pages do I have, and then they sort of sum them all up. And that could be done very quickly.
I don't know if I'm remembering this correctly. So Hadoop goes with MapReduce, correct? Yeah.
Well,
it doesn't have to anymore, but they were invented to go together. Yes.
Originally, it was the Hadoop file system, and you would run MapReduce on that. Then all the other Hadoop toys, like Spark, Hive, Zookeeper. There was a whole ecosystem around Hadoop, but now you can run Spark and on like AWS S3, you can run it on a bunch of other file systems. By default, it goes to Hadoop. Hadoop's just a file system. It's just a distributed file system, but you can run MapReduce and you can run Spark on other ecosystems now.
In my mind, I remember the three concepts that kind of go together for me with Hadoop and MapReduce was I thought that the motivation for both of those was kind of focused on the failure across many systems. Is that correct? So if you have many systems, if you have 1,000 systems and they're all doing some sort of query, and then you get one system that fails, it was about making it so that the entire thing didn't fail.
Yeah. Hadoop, but Hadoop distributed file system replicates data 3 times. So it's across different nodes. So if let's say you have 1,000 servers and just a server goes down every day, it will there's a master node which is also distributed, and it will when it notices when the nodes goes offline, it says, oh, this went offline, you should copy other data from these other nodes and put it onto new data. So it's mirrored. I don't think if enough systems go down, then you'll have a problem. But as long as you design the cluster properly and you distribute it in different data centers or different availability zones, you shouldn't have a problem. The problem what might come up though is eventually consistent. So I don't think it's strongly consistent. I don't think it's ACID compliant. So if you had, a Hadoop, a massive Hadoop cluster, and then a fourth of your cluster goes down, and then you run a query while it's mirroring the data, there might be some lag before it's replicated again if enough clusters went down. But it ideally, if it's not like very, very read intensive and you don't have very you don't have a deadline on when to get the data, there should be no problem.
I think, yeah, Ryan, there's two aspects to that. So one is that Hadoop and MapReduce had to be written in a way that they were fault tolerant, so they could handle these failures. But the other thing that I've read, I was not using it a lot at the time, but that software and hardware back then were much, much less reliable than they are now. And so if you had 1,000 nodes, you could pretty much guarantee that in the span of like 1 minute, one of them was going to fail. Like it wasn't like we can handle if something fails. It's like, oh my God, how long is it going to take, because nodes are failing all the time while I'm in the middle of this computation. And that's the reason why the original MapReduce Hadoop program, after every reduce, it wrote the results to disk, because failures were so common that the cost of redoing computation after you you use the replication to reconstruct missing data, the penalty was really severe. And that ultimately, as hardware and software got better, ended up being a bottleneck for Hadoop, because writing to disk after every operation is just ridiculously slow. And so that's the reason why Spark 1 beat the pants off of Hadoop MapReduce, because it did everything in memory. And hardware had gotten better. And at that point, if you had a node failure every 10 minutes, it was actually faster to just reread all the data, redo the computation, than to constantly be writing everything to disk.
Yeah, it's also a fun sort of intersection of two different engineering outcomes that you're looking for, which is, I'd like to run a bunch of different queries across this. So I need to replicate my data anyway, so that multiple people can run map and reduce operations, right, on the same data point without waiting for each other. And I also need this fault tolerance that Ted was just talking about, right, where nodes can go down during a query and my query will still complete. That's kind of neat that those two things got solved essentially in a similar way, just replicating the data across.
Is it fair to say Hadoop actually is becoming less popular in recent years? I don't hear that being mentioned as often as like 5 years ago.
Well, there's a lot of managed tools now. So there's a bunch of, in the cloud providers, they have all managed Hadoop-like ecosystems like AWS is EMR. They also, you can run MapReduce and Spark queries on S3 now. And that's just AWS. Google Cloud has a whole suite of big data or Hadoop-like tools. Azure does too. I'm sure IBM and Alibaba Cloud do. And then there's Databricks, which is I think it's actually now part of Azure, but it's a whole Hadoop Spark ecosystem. I mean, it was a very new technology 5 to 6 years ago, so there was more hype around it. But I still think it's around. It's just I don't think the hype is still there. Like I still think it's highly used, but it's not as cutting edge as a convolutional neural network is in 2020.
Yeah, and I feel like it's sort of like rocks, right? Under the hood, all the copy machines and scanners are using similar technology to a copier, right? But people aren't necessarily still calling them Xerox. Maybe Xerox is a bad example because people use Xerox all the time, but like there's an underlying technology that's pretty much universal across all these different vendors. And Hadoop has kind of established that beachhead. They've all done their own thing with it, but it's more around than ever, right? It's just not it's not the brand that's being sold.
I think all large data is going to be distributed across multiple boxes, and it's going to be replicated for redundancy so that, like protection against failure. I think what still is somewhat unique when we talk about Hadoop, we're talking about the fact that these are general purpose machines in the cluster. So where the data lives, you can also do computation on that server. Whereas if you talk about Amazon S3 buckets, you generally think of it as dedicated to storage. It's doing distribution, it's doing redundancy so that you don't lose stuff, but you're not ever going to actually like send a computer program over to where the data is stored in S3 to say run some computation and then return a result. So I think that's where people still want to do that. So Spark, for example, still uses Hadoop because it wants to send computation out to different nodes and then bring back results.
Yeah, that's a good point. There's definitely been a trend to decouple compute from storage, and that's driven a lot of cost gains. That's a good call out.
And if anybody's kind of like swimming with the terminology, I think we're going to see these over and over again from different lenses, different angles. So first we're going to talk about data, and then the next part we're going to talk about distributing it. And so it's going to talk about replication, sharding, different things. And so the good news is if all this isn't completely sinking in, I think there's going to be a certain level of repetition where stuff, when we see it from different angles, will start to make more sense.
Yeah, I haven't read far ahead, but my assumption is this is just giving us an overview, and then in later chapters we're going to dig in a bit more and they'll explain things more deeply. Because that was definitely my impression, where it was like, if I definitely don't have the deepest knowledge of databases, and going into this, it was like, okay, I recognize that word and some of that concept, but I think if I was going in completely blind, I think it would be pretty overwhelming, because there's just a ton of different terms and they explain like a paragraph worth of it, but they don't really say the whole motivation or how it's used or anything like that. So hopefully we see more of that description later on. What's our end time on this, Ted?
So officially I scheduled it until 1:15. So like
okay,
1 more minute, whatever. I don't think anybody who arrives at 1:15 for the Kaggle stuff is going to, throw a fit if we're running a few minutes late or whatever.
Okay, I'll try to get through this though.
Yeah.
So then they talked about the graph-like data models. So they were saying that's better at handling many-to-many relationships. The example they used was Facebook. They have one giant graph that has their vertices being people, locations, events, etc. And its edges are the connections between all of those. So a person went to this location or this event, or they have this relationship to this other person. And that's all captured in their one big graph. And then they talked a little bit about the different options in terms of graph models. And so they talked about property graphs and triple store. And then they talked about the languages to query those graphs. So there's Cypher, SparkQL, Datalog for querying those. And then they spent a little bit more time talking about property graphs and the way that they're organized. So they said they've got the vertex, which has an identifier. It has outward edges and inward edges. And then it also has a collection of properties. And then looking at the edges have an identifier. They have a starting point of the edge and they have the ending point of the edge. So they called those the tail and the head, showing which direction the relationship was going, basically. And then they have a label to describe what that relationship is. And then they also have a collection of property. And so in this one, there's no real schema. Everything is just kind of interconnected. You just say this thing has this property, which is related to this other thing that has this other property. And you can also do queries and all kinds of different things in multiple different languages or in multiple different directions. So you say this person is from there, or you could also say this person has, or this location has this person, basically. You can go both ways on the relationship. And they were showing that that's good for certain kind of nested things, like location, where you might have a city that's inside of a state that's inside of a country, and then you can kind of map all the way down to the most granular or the least granular. And you can also connect that to people potentially. Then they talked a little bit about the Cypher query language. They had some examples of those, and they basically showed the query is formatted in a way that's basically saying, find all the people who have this condition of this property and this other condition of this other property. And so you can say, are they born in the US and live in the EU? And then it will basically search the whole graph for those two conditions and then return the samples that have those specific conditions met. And so you can look at that in multiple different ways. And they were showing basically you can go either direction. You can start at the US and you can look at born in and then find all of the outward connections, or you can look at all of the people and find all of the ones that map into born in the US. And then they showed an example doing graph queries with SQL, and they showed it's like a whole page of code, and it's pretty difficult to read through, and it's difficult to write probably. And it requires calling the same thing multiple times, basically, to dig deeper and deeper until you find the end of it. Then they talked about triple stores and SparkQL. And so they're basically saying that the format of the triple stores, you have your subject, your predicate, your object. The example they used was Jim likes bananas, Jim being the subject, predicate being likes, and the object being bananas. And so you're showing basically the relationship and what kind of relationship by using that format. And then they talked about RDF, Resource Description Framework. And so some people had this idea, the semantic web, where everything can kind of be interconnected by all of these concepts, and you can map from one website to the other and kind of intermingle all of this information, but it hasn't really gained a whole ton of traction. And then they were saying that it's fairly similar to the query format of Cypher. They had the two examples side by side and they look fairly similar. And then they also noted the additional example of data log, and they were kind of just saying, this is kind of the same thing, but older. This preceded the other ones. It's not necessarily used, but it's kind of historically relevant. I think that's all I have. Anyone have any questions, things to add? I haven't really worked at all with graph stuff, so most of that is new to me. We had Hobbs at one point give us a kind of crash course on the triple stores, so I was somewhat familiar from that, but other than that, it was new to me.
There's new graph databases that came out in the cloud too. So there's actually met a guy who has a managed Neo4j. He founded a company. He tried to hire me a few years ago. It's called Graph Story, but they do manage Neo4j, which is the most popular graph database in the cloud. But like at reInvent this year, Neptune is a graph database by AWS, and they're using something called Gremlin, which is an open standard for graph databases. Apparently you can use it with Neo4j too. So Cypher is the proprietary language for Neo4j, and apparently you can do more joins with Neo4j. Like you can do like joins out to like 5 or 6 connections, where I don't think you can do that with Neptune. But to my knowledge, in the last 2 or 3 years, only graph databases I've heard people use but weren't proprietary, like built by Facebook themselves, whereas Neo4j and Neptune. Granted, this book is a few years old, so probably back in like 2012, there were other ones being used. But in the last like 5 years, I've only heard of Neo4j and Neptune being used outside of the proprietary graph databases at like Amazon and Facebook and Twitter.
A while ago, there was a talk in the San Diego area. I forgot which meetup group put it on, but they had a presentation from Neo4j, and they were showing how the Neo4j database was used to look at a whole bunch of relationships to detect fraud or something along those lines. And it was a pretty interesting demo. And they were showing we made this certain query 10,000 times faster. And if we tried to do this with SQL, it would be so slow and painful, and we couldn't possibly look in the depth that we did. So it's interesting to see the applications of that stuff. I think you have to be pretty adept in the technology to get good use and to know when it's applicable, though.
There's so there's graph files. There's a graph visualization tool called Giphy. It's like Tableau, but for graph databases or graph files. It's GEPHI. It's an open source tool if anyone's interested in that. I've also heard, so like I know IRS uses graph databases for like fraud, and I know there's a lot of law enforcement and intelligence gathering, but I've also heard it being used in like pure like industrial engineering. So like a undisclosed engineering company had a bunch of sensors throughout their factory to detect anomaly, and they use Neo4j to connect with different sensors. So if a certain group of sensors went down, they could find out exactly where in the factory it went down, or if it detected something. That was just one use case. You always hear about social network and intelligence gathering, but there are uses outside of that for graph networks.
Interesting.
And by the way, so the next chapter I haven't finished reading. I started a little bit. It talks about, well, how do these different databases work under the hood? So I don't know how much it's going to talk about the graph databases, but I know it definitely is going to talk about how relational and some of these other things work under the hood. And so, like Becky asked a question earlier about, well, what would be faster? So at the end of the day, right, nothing is faster inherently about it's a graph with triple store or it's relational, right? It's when you actually have to run that algorithm that says find all the people born in the USA but who emigrated to Europe or whatever backwards, that's when the ultimate performance question, gets answered. So depending on how much they talk about graph databases, we'll see a little bit more. And then I don't know, Ryan, if maybe I just put it on my wish list to try and get a speaker talk about graph databases.
Yeah.
So I just Googled very quickly on the applications for a graph database. And so one of the things that is mentioned there is a recommendation system. Do you guys have any point of view about why graph database will be a better, it will be better suited for that kind of application?
Yeah, they work well for recommendation systems. You can still use a neural network to do that. And there's actually, just a few days ago, they're trying to do neural networks with graph databases. I don't know how that works, but they were using some sort of new neural network that uses the graph structure, and specifically for recommendation systems. Recommendation systems is probably, that's another common use of graph databases, but you can also use like tabular data and do just a traditional recommendation system with a neural network, but it depends what you're trying to do.
Yeah, one of the folks here in San Diego founded it's like a service that takes musicians booking gigs at like bars and clubs and stuff. And so his business, he needs this sort of recommendation, right? But he doesn't necessarily need something super predictive at this point. He just wants to be able to make those hops, right? But once he has, say, 1,000 businesses and 10,000 gigs in his system, right? A relational DB, because he just kind of wants to do this massive cross join across everything to get the things that he should recommend to this bar because it's down the street from that one, right? Or it's similar in some way, become really computationally expensive. So that's an example of sort of a, it's not as compute or prediction intensive as a neural network, but it's a good fit for a GraphDB.
Do you guys know, isn't there like some clustering algorithm that runs on graph databases a lot faster than if you just do standard clustering on tabular data?
Yeah, there's several algorithms. I have a book on it. I might grab it, but it just depends what type of algorithm. There's a bunch of certain algorithms run a lot better on graphs, specifically for recommendation system clustering. Like I was told for like intelligence agencies, when they try to detect like terrorists to prevent the next 9/11, they tried to use a bunch of graph databases, and you basically just look at the edges between the nodes. Like it's not even the attributes themselves, but they look at certain activity. They use Facebook you used to be able to download your friends list as a graph file from Facebook. I just posted the visualization tool Giphy, but like a few years ago, I visualized my friends list, and I could see, oh, these are my friends from college, these are my friends from high school, these are my friends from work, these are these other friends, and I could like separate them out, and you could apply a clustering algorithm. So you could, and it would, you know, using this algorithm, it would color with different nodes, base it into clusters. You know, it'd be like k-means, but for graph databases, and it could just tell by how they were connected, they would cluster them into different groups.
Maybe you're thinking of the 6 degrees of Kevin Bacon, Ted.
It's similar to that.
That's got to be cheaper on a graph database than a relational. I wonder too if what you're talking about, Ted, ends up being more about the transformation step rather than the actual, you know, gradient descent or whatever. Just try to find like if you're doing k-means or something, right?
I don't remember. I think I just saw somewhere in a talk they were doing some kind of clustering, like Keegan's saying. Like you can cluster your friends into, you know, if your college friends not only know you but know each other, then, you know, based on whatever, you can quickly see like that's, you know, cluster 1. And then these other high school friends know you and they know each other, but they don't really know your college friends. That's cluster 2, and that kind of a thing. All right, so so next week we'll be talking about chapter 3, and again, I haven't finished it yet, but hopefully some of these questions will be a little bit more approachable because we'll actually look at the data structures underneath, and I'm sure it'll just raise other new questions about, but wait, how about this, and what if that, and whatever. But I think that's the point of this book, is to get an appreciation for these different design trade-offs. And again, when you have, especially when you have a large data intensive application, and you can't afford to just, you know, kludge over it by throwing more, you know, horses at the problem.
So swapping over to Kaggle stuff now, are we making that transition?
Yeah, I think that's the plan. So we're gonna see how long we need to talk about a chapter and try and figure out, you know, we don't want to take too long, you know, but if we keep running over, maybe we add another 15 minutes or something like that. But so yes, so we have the book discussion and now the Kaggle and projects competition back to back. And then again, it's 1:30, so in 2.5 hours at 4 o'clock, we're gonna have Bernard Lee talking to us about machine learning in fintech. So for those of you who want to stay, you can stay now, and we'll talk about Kaggle stuff we'll see. I mean, about 45 minutes. If people have lots they want to talk about, that's great. But otherwise, you know, approximately 45 minutes.